We are in section 7.7, approximate integration. There are two situations in which it's impossible to find the exact value of a definite integral. First one is you cannot find the antiderivative, and the second is going to be data is collected or obtained from an experiment, and there is no formula for the function. So we're going to look at both of these, but before we do that, we're going to get an understanding of exactly how to approximate an antiderivative. So first thing is we can use left, right, and midpoints. And what we're going to do is approximate that area under that curve. And so to do that, we're going to make rectangles. But determining the height of the rectangle, we're either going to use the left side of the interval, the right side, or the midpoint. And so I'm going to zoom in here to look at the left in approximation. And so with this, I'm going to go ahead and say that our graph is starting and ending at A and B. But I'm going to call this also x naught, which is going to be the same thing as A. And my last value over here where that interval is going to end is going to be x sub n, or B. And then we're just going to split this into equal pieces. They're going to be equal widths. And I'm going to call it x1, x2, we'll say x3, and say dot 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 all the way through until x sub n minus 1. And so in order to approximate the area here, I'm going to use left endpoint. So that means I'm going to go up to the height of the left endpoint, draw a line over, and this is going to be the first rectangle that I can find. And then likewise, I'm going to do this again for the second rectangle, going up to the left endpoint, going over, and then that area I can easily find. And then for the next one, up to the left endpoint, over, and then again, this is our area that we would find. And this continues on until we get to the last interval here, and my left endpoint, over and down, and then adding in this area also. And so, using this idea, we have a left endpoint rule. This is our left endpoint approximation. And this is going to be L sub n is equal to the integral from a to b of f of x dx. And this is going to be the sum from I equals 1 to n of f of x sub I minus 1 times delta x. So that delta x is our width, and the f of x sub I minus 1 is going to be the height of each rectangle. And so for this, we would have delta x times each of these heights. So I'm going to pull that delta x out, and so we have f of the first one, which is going to be x sub 0, plus f of x sub 1, plus, and say dot dot dot. And then the last left endpoint that we had was x of n minus 1. Notice that we don't use x of n in our picture up above to define any of the heights for left endpoints. And then delta x is defined by that width. And so in order to find the width, we would take the difference there between a and b, so do b minus a, and then divide it by however many rectangles we have. And in this case, we have n rectangles, so dividing by n. Remember that those rectangles are equal width, so delta x is going to be b minus a over n. And then I'm just going to bring the rest of this stuff down. And that the f values, our function values, are our heights of those rectangles. And again, we're using left endpoint approximation. So this is how we would use the left endpoint rule or approximation in order to estimate the area under a curve or the antiderivative. Next, we're going to look at the right endpoint approximation, which is the same idea. Notice that curve is exactly the same, and we are still going from A, or we also define it as x naught, all the way down to b, or x of n. And again, these rectangles are going to be of equal width. So I'm going to put down x of 1, x of 2, x of 3. And then I'll also put on our x of n minus 1, and again dot 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 because you have all these different rectangles on there. So this time we're using our right endpoint approximation. So I'm going to start on the right this time of my graph. It makes it easier for me to see those rectangles. So the right endpoint in over, in shading, you can see that area you can calculate. Likewise, from x of 3 is the height of that third rectangle and over, using that as my height, and I can find that area. For x of 2, that height and over, and I get that height here. And then x of 1, and then over. And this time notice that we did not use x naught. So r sub n, or my right endpoint rule, is of the integral from a to b of f of x dx, is going to be the sum from I equals 1 to n of f of x sub I times delta x. And notice this time it's f of x of I, and the reason why is because we don't start with that 0th term, so x of 0. Well, this time we actually go through x of n. And so that delta x we can pull out in front, and the first value we would have is f of x sub 1 plus f of x sub 2 plus all the way through that last height is defined by f of x sub n, since we are using those right endpoints. Likewise, delta x is that width that we have on here, which again we discussed is b minus a over n. So that's the width times the height. And adding these all up, we will get the total approximate area under that curve, or that antiderivative of that function. So these are the two rules that we have, the left and the right endpoint rules. And then we also have a midpoint approximation, which is actually the best one to use. So for the midpoint approximation here, we have the same graph, so divide it the same way. So x naught would be my A, and x sub n would be my B. I'm going to go ahead and zoom in here just so we can see our graph a little bit better. I'm going to put on my rectangles. So I have x1, x2, x3, and I'll put on x of n minus 1 and put my dot dot dots. And so for this one, and what I'm going to do is I'm going to go ahead and draw on where those midpoints are. And I'm going to call the midpoint on here, this part right here, is x sub 1 star. And so I'm going to go straight up to where that midpoint at x sub 1 star hits that function, and that's going to define the height. And so this is my height of my rectangle. Likewise, the next one that I have is going to be x of 2 star. And again, going up until it hits the function, and then going over and down, we get that rectangle there, so we can add those together. And then likewise, we would have x of 3 star, which is, again, going up to my function. That's defining the height. Drawing a line down and finding that area of that rectangle. And then the last one that we have here is going to be x sub n star, which again, defining the height of the function there, that rectangle, and then shading that area. And so for this, our midpoint rule that we have is going to be the sum from I equals 1 to n of f of x sub I star delta x. And again, remember the x sub I star is that midpoint as defined by my picture. Likewise, I'll factor out the delta x, which again is going to be the width, which is still the same delta x as defined up above. And this is now going to be times those heights, which is defined by those midpoints. And we know that delta x is the same as b minus a over n times, again, those heights. And from here, we know that we can just define where x of I star, you would find by adding together those two values for the rectangle, so x naught and x1, dividing by 2, we get x1 star. So I'll put that down. And this is the midpoint of that interval, which is going to be from x of I minus 1 to x of I. On the next page, we have trapezoidal approximation. So this is going to be using trapezoids rather than rectangles to approximate the area of each of those subintervals. And so the first thing is that to remind us about the area of a trapezoid. And that's going to be equal to 1/2 the height times base 1 plus base 2. And so going ahead and sketching this, same curve, exactly what we had before. I'm going to call this x naught. This is equal to a, and our ending one will be x of n equal to b. I'm going to zoom in here just so we can better draw this. And so I have x sub 1, x sub 2, and x sub 3. And again, those widths are going to all be the same. And then over here we have x of n minus 1. And so the first trapezoid that we have, the height is actually going to be our delta x. And if you were to draw a trapezoid here and tracing it, and I'll shade it, that would be our first trapezoid here. And so our base 1 would be the function evaluated at x naught, and then base 2 would be the function evaluated at x1. For the next trapezoid, drawing that in, I'll go ahead and shade it. And again, our height's the delta x, and then the function at x1 is going to be base 1, and the function at x2 would be base 2. And so you would continuously do this, drawing again the next trapezoid here. We could shade it, and then all the way through to that last trapezoid that we have. And we would sum these all up. And so looking at our formula that we have over here for the trapezoid rule, and so notice that it's t sub n is that number of intervals that we have. And it's going to be the integral from a to b of f of x dx, which again is approximated by, and we have a 1/2 in our area, times h, which is our delta x, and then times base 1 plus base 2. And again, adding those all up, so we had f of x naught plus f of x1, then x1 was f of x1 plus f of x2. And if you notice, there's two f of x1s. So we're going to have f of x naught plus 2 times f of x1 plus 2 times f of x2 plus dot dot dot, continuing on, and we'll say 2f of x of n minus 1 plus, there would only be one of that last base, which would be f of x of n. And again, where delta x is equal to that height, which is going to be b minus a divided by n. And this is the trapezoidal rule that gives a better approximation typically than that midpoint. And then the next approximation rule that we have is Simpson's. And Simpson's, this is going to use parabolas. So in order to graph a parabola, we need not just 2 points like a linear line, we need 3. So I'm going to go ahead and zoom in here on our graph. And so this is going to use parabolas. So we need 3 points to make a parabola. So similar idea, still going to have x naught, which is my a, and my x of n, which will be my b. And approximating this, I'm going to go ahead and put, we'll say x1, x2, x3, I'll draw another line on here, x sub 4, and again those equal widths. And so for Simpson's approximation, we need to make a parabola. And so the first parabola we would have using those 3 points that you see here would be a parabola, and we'd be able to find that area under there. Likewise for the next 3. And likewise for the next 3. And this would be our approximating. And this gives us the best approximation. And so we can sum this up. A little note though is that in order for Simpson's approximation to work, n must be even. So Simpson's rule that we have, S of n, again, n is that number of intervals that we have, and n again has to be even. And this is going to be delta x over 3. And then we have f of x naught plus 4 times f of x sub 1 plus 2 times f of x2 plus 4 times f of x3 plus 2 times f of x sub 4 plus, and then that last term we'd have 4 times f of x sub n minus 1 plus f of x sub n. And we will discuss this a little bit more in class and a little bit about a proof of this formula that we have. So we have 5 different ways to approximate the area under a curve or approximate an integral. And that's going to be using left endpoints, making rectangles, right endpoints, making rectangles, midpoints with rectangles. We have trapezoids approximation or Simpson's approximation, which uses parabolas. And we also have down here error bounds. And so it says, suppose that the second derivative of x, the absolute value of it, is less than or equal to k. For a less than or equal to x, less than or equal to b, the error bounds for trapezoid and midpoint are errors in which the trapezoidal and midpoint rules then, and notice the T for trapezoid and the M for midpoint, and you can use when asked to estimate errors, since these are approximating. So to estimate errors, so looking at those formulas, you'd see that our absolute value of the error for the trapezoid or midpoint rule is going to be less than or equal to that numerical value that we get, where k can be any number larger than all the values of the absolute value of f prime of x, but smaller values of k give better error bounds. In general, the trapezoid rule, the error for that would be the integral from a to b of f of x dx minus that approximation. And likewise for our midpoint rule would be the integral from a to b of f of x dx, the actual value that you would get, the true value, minus that value that we got using our midpoint approximation. So you can also use these two when asked to find errors, to estimate those errors. And then on the next page we have the error bounds for Simpson's rule. And so it says, suppose that f to the fourth, the fourth derivative of x, the absolute value of it is less than or equal to k, for a less than or equal to x, less than or equal to b, if the Simpson's error, E sub s, is an error involving in use of Simpson's rule. then the absolute value of that error is going to be less than or equal to, and we have k times b minus a to the fifth all over 180 into the fourth. And again, you can also approximate it by taking the true value minus what you get from your approximating sum using the Simpson's rule, and that will give you the error. So looking at the next example, it says part A, find the approximation t sub n for the integral from 1 to 2 of e to the 1 over x dx. And so for this, we have a t here, meaning it's using the trapezoidal rule. And also the 10 down here that we have, I'll circle that. And this means that n is equal to 10. And we're going from 1 to 2, so if you were to think about the graph of this, we have to start at 1. It's exponential. It's going to decay. Something along these lines. And our delta x value would be equal to b minus a over n. And so 2 minus 1 over 10, or 1 over 10. And so we're going to be counting by 1/10. And so we have 11 over 10, since 1 is the same as 10 over 10. Then we have 12 over 10, 13 over 10, 14 over 10, 15 over 10, 16 over 10, 17 over 10, 18 over 10, 19 over 10, and then 20 over 10, which is equal to 2. So that would be our last value here. And again, you can see that splitting those into those pieces. So we are making trapezoids for this problem. And so to approximate this, and I'll go ahead and put down part A over here, I'm going to have t sub 10. The formula starts off with 1/2 times delta x, and delta x we just calculated was 1 over 10, times, and then we have to do f of our starting value, which is f of 1, plus 2 times f of x sub 1, or the next value, which is 11 over 10, plus 2 times f of 12 over 10, plus dot dot dot, plus all the way through to 2 times f of 19 over 10, plus f of 20 over 10, or f of 2. And that's by that formula. So for the trapezoidal rule and for any of these approximations, it's a lot of button pushing on your calculator. And so our function that we need to substitute this into, our f, and I'll write that up above, f of x is equal to our integrand, which is e to the 1 over x. I'm going to go ahead and I'll just round 3 or 4 decimal places. I'll say 4, and a lot of button pushing. So we have 1 over 20, and then f of 1, get 2.7183 plus 2 times 2.4821 plus 2 times 2.301 plus 2 times 2.1581. Continuously doing this, 2 times 2.0427 plus 2 times 1.9477 plus 2 times 1.8682 plus 2 times 1.8008 plus 2 times 1.7429 plus 2 times 1.6927 plus 1.6487. And so we get 1 over 20, multiplying and adding all those together in the parentheses, we get 40.4394, which works out to being 2.02197. So that's our approximation using the trapezoidal rule. Part B says estimate the error in the approximation of part A. And so in order to do that, for the trapezoidal rule, which was on the bottom of the previous page, we need to find, for the trapezoidal rule, the second derivative. And so our first derivative is since our function is e to the 1 over x, so our first derivative is equal to the same function times the derivative of the exponent, which would be negative x to negative second. So then our second derivative, we have to now use the product rule in addition to the chain. And so we have e to the 1 over x times, it's going to become 2x to the negative third if you take the derivative of the negative x to the negative second, plus writing down the first thing that we had, which is negative x to negative second, times the derivative of the first, which is e to the 1 over x, times the derivative of the exponent. So from here, we get 2 over x cubed e to the 1 over x, plus we're going to end up with 1 over x to the fourth e to the 1 over x. So we're able to factor out 1 over x to the fourth, and also an e to the 1 over x, and we'd be left over 2x plus 1. And from here, from the formula on the previous page, it says suppose that the second derivative, the absolute value of it, is less than or equal to k for x in between a and b. And in order to find this k, it's going to be any number larger than the values of the absolute value of our derivative, but smaller values of k give a better bound. And so we're going to look at where our second derivative here, evaluating at our endpoints, and working out, and you should see by our function is decreasing concave up, but looking at our values here, we're going to end up with 1 over 1 to the fourth e to the first times 3. And then our second one is going to be 1 over 2 to the fourth e to the 1/2 times 4 plus 1 is 5. And so working out our first one, we get 3e, which is equal to about 8.15. And our second one we get is equal to 0.515. And so we're going to use this value, or actually the 3e, without it simplified, to approximate our error. And so this would be our k value for our function. And so our error, which is going to be the absolute value, less than or equal to k times b minus a to the third over 12n squared. And so we have e of t, the absolute value, less than or equal to k, which is 3e, 2 minus 1 to the third, all over 12 times 10 squared. And this is going to work out to being 0.0067957. And so this will be our error. And again, we chose the value of 1 for x to substitute into the second derivative, and the reason why is because our function is decreasing on that, and we get a larger value there and a larger bound. So next thing is for part C. If you look back up above, part C says how large do we have to choose n? So we need to choose n so that the approximation T sub n to the integral in part A are accurate within 0.0001. So we want our error, which we know is 3e 2 minus 1 to the third all over 12 times n squared, since this time it's asking for us to find n, would be less than or equal to that error within 0.0001. And so to solve this, I'm going to multiply both sides by 12n squared. So we get 3e is less than or equal to 0.0012 n squared. And then dividing by the numerical value in front of the n squared, we get n squared is greater than or equal to 0.00123e, or n is going to be greater than or equal to 82.44, or n, since it should be a whole number, be greater than or equal to 83. So we would choose n to be 83. And so we would have to have 83 intervals here and to make our error approximation within 0.0001 of the actual true value of it. So on the next page we have another example. This one says find the approximations m sub n and s of n for n equals 6 for the integral from 1 to 4 of 1 over the square root of x dx. Then compute the corresponding errors e sub m and e sub s. What observations can you make? So really quick, m is using midpoint and s is using Simpson's. So first thing is our function is definitely decreasing here. We are going between 1 and 4. And so we had 1 here, 4 would be our ending value. And we need to find m sub 6. And in order to do this, we first need to talk about what delta x is. So I'll go ahead and put delta x up here, which is b minus a all over n. So b here is 4 minus 1 over 6. It's just 3 over 6, which is 1/2. And so the next one that we have would be 1.5. And then we would have 2, 2.5, and so on. And since we're dealing with midpoints here, our midpoint between 1 and 1.5 would be 1.25. The next midpoint that we would have is 1.75, and then 2.25, and so on. So for our midpoint rule, the formula is going to be delta x, which for us we already calculated is 1/2, times f, and we're going to be evaluating this at all the midpoints. So the first one we have is 1.25 plus f of 1.75 plus f of 2.25 plus f of 2.75 plus f of 3.25 plus f of 3.75, which would be our last one. And then again, our function here, f of x, is our integrand, which is 1 over the square root of x. So a lot of calculator pushing, button pushing here. So we have 1/2 times, and I'll go ahead and round 5 decimal places. So f of 1.25 is going to be 0.89443 plus 0.75593 plus 0.66667 plus 0.66302 plus 0.5547 plus 0.5764. And so from here we have 1/2 times 4.001191, which is going to work out to being 2.0005955. So this is our approximation using the midpoint rule. It also asks for us to use Simpson's rule, so I'll go to put S of 6 here. And Simpson's rule is going to start off with a delta x over 3. And so we have 1/2 over 3. And then we have f of x naught. So f of 1 plus 4 times the next value that we have, which is f of 1.5 plus 2 times f of 2 plus 4 times f of 2.5 plus 2 of f of 3 plus 4 of 3.5 plus f of 4. So 1/2 divided by 3 would be 1/6. And then again, putting all these values into your calculator, f of 1 is just 1 plus, we have 4 times 0.8165 plus 2 times 0.70711 plus 4 times 0.63246 plus 2 times 0.57735 plus 4 times 0.53452 plus, and then f of 4 is going to be 0.5. And so for this we get 1/6 times 12.00284, which approximately is going to be 2.0004733. So this integral that we have, we are actually able to integrate it using what we know from class. And so I'm going to go ahead and say, well, let I equal the integral from 1 to 4 of 1 over the square root of x dx, which is equal to the integral of 1 to 4 of x to the negative 1/2 dx. And integrating this, you're going to have x to the positive 1/2 times 2. And we're evaluating this from 1 to 4. And so evaluating this, we have 2 times the square root of 4, 4 to the 1/2, which is 2, minus 2 times 1. And so this works out to having 4 minus 2, or just 2. And that's what our actual area under the curve is going to be. And so to look at the errors, which is what it wants us to also do, is find the error at the midpoint. We're going to take I minus what we got using the midpoint rule. So we have 2 minus 2 point, and we calculated it as 0.05955. And so we get negative 0.0005955. Likewise for Simpson's, our error. So the error for Simpson's is going to be I minus what we calculated for the Simpson's rule. And so our actual area was 2 minus what we calculated for our approximation. Putting that down, subtracting, we get negative 0.0004733. And so the smaller error that we have is the one that we actually got from Simpson's. And so it says, what observations can you make? And we can say smaller, the smallest error is with Simpson's rule. So that gives a better approximation. So right below this, it says Simpson's rule is a powerful numerical technique used to integrate functions represented by data. The formula given in our textbook for Simpson's rule assumes that all the subintervals are of the same length. That was delta x is equal to b minus a over n. If the subintervals are not of the same length, we must use the trapezoidal rule. Considering the quality of the Simpson's rule approximation, a researcher would be wise to design their data collection in such a manner as to ensure the creation of an even number of subintervals of equal width. And that's because that Simpson's rule gives such a better approximation. So there's another example, an actual real life example, and the usefulness of this that I'm going to go ahead and circle, and we'll talk about this example together in class.